All right, so welcome to multivariable calculus. This is lecture 27. And what we're going to be doing today is we're going to be discussing the roots test, the ratio test, and then we've already talked a little bit about Taylor series. We'll talk a little bit more about Taylor series and eventually get into some hopefully fun applications of it. The idea of Taylor series is to take something that's very complicated and expand it in terms of a bunch of simpler items. And the hope is that you don't need to have an infinite sum to have a pretty good knowledge if you just have a large number of terms that's frequently pretty good. At an event last night, I was talking with some students about how well can you hear music. So when you have a CD and you have some types of compression of information, is it really bad for the average listener? Can you really tell the difference? Now, some people have a terrific ear and they claim that they can hear the difference between $1 million violin, a $50,000 violin, and what you would see a kid playing in a band in high school. I am not one of those people. But there are some things, once you're trained to hear the small differences, you will always find it. How many people know about the arrow hidden in FedEx? So once you know that it's there, it's hard not to see it every time you look at it. And a lot of companies have things hidden like that. The Big Ten Conference has an 11 hidden in it because for a while there were 11 teams in the Big Ten. So once you know to look for these things, can you train yourself to actually listen and hear these very small differences? But the hope is that for many things, you can get a good enough approximation for practical purposes by just looking at a few terms. If you look at a lot of real world problems, when you're trying to figure out, for instance, what schedule should the airlines fly? Well, we're trying to predict what demand is going to be months in advance. This is hard in general. In the post-COVID era, it is even more challenging to try to predict. So what do we think restrictions might be like and how comfortable do we think travelers might be? Summer months I have reasonable confidence about, but next November, December, January, I'm not that optimistic about predicting what travel will be like as we get to another set of cold months. And so how do you try to figure out what you want to do? Well, we have some very complicated algorithms that we can use. But given the uncertainty in the inputs, I'm not so concerned if I have a few issues with just trying to estimate what the answer should be. All right. So the big thing we've talked about so far is we've talked about the comparison test. The comparison test is wonderful. If you have a non-negative sequence and it's less than or equal to term by term from some point onward of something that converges, then the sum converges. If it's greater than or equal to from some point onward from something that diverges, then it diverges. So as long as you can figure out what to compare it to, the comparison test is wonderful. The trick is you have to figure out what to compare it to. And so the hope is, can we find a way to do these comparisons easily? Sometimes what you do is you take your series and say, well, this is the main term in the numerator, so I'm going to just throw away everything else in the numerator and just focus on this. Well, I can't just throw away everything else. Maybe I'm going to multiply the numerator by a factor of 100. And that's not going to affect whether or not it converges. It will just affect what it converges to. Right. So we stated the ratio and root tests last time. So it would let rho be the limit if it exists as n goes to infinity of an plus 1 over an. And if this is less than 1, it converges. Greater than 1 diverges, equals 1, no information. And as an example, rho equals 1 for an equals 1 over n, and an equals 1 over n squared. So that's enough to show you that there really is no information. It could be that the proof that I give you says that we have no information as to whether or not it converges or diverges if rho equals 1. But in practice, if rho equals 1, it always diverges. It could just be that the method of proof I'm giving you is not strong enough to do that. No, there's no hope. I can give you an example where rho equals 1 and it converges. I can give you an example where rho equals 1 and it diverges. So there really is no information when rho equals 1. So if you do this calculation and rho equals 1, then this means you have a screaming baby and what you tried does not work. So you then move on to something else. This is not the test that you're looking for. You need to move on to another test. All right, that one was, I guess, too obvious for reference. All right, so let's see why the ratio test is true. So the ratio test compares to a geometric series. I will do one case. I will do either rho is less than 1, or if you really want me to, I'll do rho is greater than 1. But you're completely free to choose which one you want me to do. Any preference? I'm going to do rho less than 1 or rho greater than 1? Less than 1. Excellent. Unfortunately, this is recorded, so people could say that this was a leading question, but okay. So here's rho. And here, because rho is less than 1, what this means is, as rho is less than 1, there is an epsilon greater than 0, such that rho is less than 1 minus epsilon. And because rho is less than 1, it's got to be some distance away from 1. I could take epsilon to be, say, 1 minus rho over 1,000. Why do I want to do something like this? Well, I know a geometric series with ratio less than 1 converges. And so I want to just make sure that I stay well away from 1. And as long as everything is bounded by a number that's strictly less than 1, I have a hope of using a geometric series. If I have a sequence of terms that's less than 1, maybe they're approaching 1. And if they're approaching 1, I can't find one ratio that works for everything. So we know the limit as n goes to infinity of an plus 1 over an equals rho. So when I write a symbol like this, this means there exists. So there exists an n such that, and this means for all. So we have the backwards e, we have the upside down a, such that for all n greater than or equal to n, an plus 1 over an is less than 1 minus epsilon. And the reason is because it converges to rho, eventually, no matter how small of a neighborhood you give me, an plus 1 over an lives in here if n is greater than or equal to n. Because it's converging to rho, so eventually it can't be too far away from rho. So I just choose epsilon so that, I choose a new width so that I stay close to rho. Everybody fine with this? Yeah, I'm converging to rho, so eventually I'm going to be no more than rho plus or minus 1 over quadrillion. Or rho plus or minus 1 over quadrillion factorial. And I just make sure that this is less than a fixed amount of 1. Okay? So let's see what's going on. So now we would have an plus 1 would be less than or equal to an times 1 minus epsilon. Does everybody agree with that? Because an plus 1 over an is at most 1 minus epsilon, so I can just multiply it. Everybody happy with this? Then let's look at the next term in the sequence. I would have an plus 2 is less than or equal to an plus 1 times 1 minus epsilon, because the ratio is at most 1 minus epsilon. But what do I know about the absolute value of an plus 1?
That it less than or equal to an times 1 minus epsilon.
Yeah, so this then just becomes the absolute value of an times 1 minus epsilon squared. If I did an plus 3, that'd be less than or equal to an plus 2 times 1 minus epsilon. So what would that be less than? Yeah, an 1 minus epsilon cubed. So it's a geometric series. And what is the ratio? So I go from term to term to term. What's the ratio for my balance?
1 minus epsilon.
1 minus epsilon, which is less than 1. So I would get that the sum n goes from n to infinity of an would be less than equal to the sum n goes from n to infinity of the absolute value of an. Because again, I can throw away finitely many terms in the beginning without affecting whether or not it converges or diverges. Yes? If I want to figure out if the sum converges, the first couple of terms don't matter. Because everything is finite, I can just throw them away. And I know each one of these, this is going to be less than equal to the sum, I'll say k goes from 0 to infinity of the absolute value of an times 1 minus epsilon to the k. Oh, this is a geometric series, right? I've multiplied every term by the absolute value of an. Is that going to affect convergence? No, I'm just multiplying everything by the absolute value of an. So this is going to just be the absolute value of an over 1 minus r. So this is just going to equal 1 over epsilon times the absolute value of an, which is less than infinity. It converges. So this is the proof that if rho is less than 1, the series converges. I can bound the sum of the tail, the sum from big N onward, by a geometric series that converges. Now, my terms an could actually have alternation in sign, but that's only going to help convergence. So any questions about this proof? So this is the ratio test. Or at least this is half the ratio test. Now you have to do, well, what would happen if rho is greater than 1? Well, if rho is greater than 1, then the ratio of the terms is going to be getting larger eventually by at least a fixed factor. So imagine rho is equal to 5. Then eventually each term is going to be at least 1.1 times the previous. So the terms in absolute value are going to be exploding. In particular, they can't be tending to 0, so the series has to diverge. So it's actually a little bit easier for the other one, because you can just go back to the fact that if the ratio is greater than 1, the term's not tending to 0. Okay, so any questions about the ratio test? So now we just have to figure out how do we actually use it. So let's do an example. We know the function exponential x, often written as e to the x, is the sum, and goes from 0 to infinity of x to the n over n factorial. So what would an be for this? If you want, it's really an of x. What would it be for this series? So I'm writing this as a sum. What is an or an of x for this sum? So you say every term is 0. Now I'm trying to write this as a0 plus a1 plus a2 plus dot dot dot, or if you want a0 of x plus a1 of x plus a2 of x. You know, I want to write this as an infinite sum. For each n, I have to tell you what is the nth term in my sum. If I give you a different value of x, I have a different sum. My sum depends on x. So that's why I'm using the notation an of x to remind myself that the nth term is going to depend on x. So what should the nth term be?
to the n over n factorial.
Yeah, just x to the n over n factorial. So let's compute rho, which is the limit as n goes to infinity of an plus 1 over an, which is the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. All right, so how would I simplify that out? How would you simplify the x part? Yeah, we have an x to the n plus 1, we're dividing by x. So you're just writing it very slowly. It's x to the n plus 1 over n plus 1 factorial, and then the other becomes an n factorial over x to the n. So this is just the limit as n goes to infinity of x. And now what about n factorial divided by n plus 1 factorial? What does that equal? So we have n factorial in the numerator, we have n plus 1 factorial in the denominator.
1 over n plus 1.
Yeah, just 1 over n plus 1. As n plus 1 factorial is n plus 1 times n factorial. So x is fixed and n goes to infinity. So what does this limit go to? Yeah, as x is fixed and n goes to infinity, limit is 0. Therefore, it converges for all x. So this is a wonderful result. We've just shown that the series converges for all values of x. So even if x is a huge number like a googolplex, we're taking it to a tremendous power. Well, if you look at x as a googolplex, as you add more and more terms in the beginning, x to the n is going to dwarf n factorial initially. A googolplex then plus, so you're going to get 1 plus a googolplex over 1, plus a googolplex squared over 2, plus a googolplex cubed over 6. So the first couple of terms you add, you're just adding more and more and more. But if you go down far enough, eventually the n factorial is going to be greater than x to the n. If I take n to be x, x to the n is still going to beat n factorial. You've got to go down much further. But eventually, the n factorial is going to beat the x to the n. Yes?
So you're saying the series defined by e to the x converges?
Converges for every value of x. That's what we just showed. No matter what value of x you take, you get a limit that is equal to 0 when you use the ratio test. So since the limit is 0, it converges. So no matter what value of x I take, e to the x is well defined, this infinite sum converges. So you always have to worry when I define something, does it make sense? And here this does make sense. It is well defined for all values. So we don't have a terrible situation where it might converge for some values and not for others. So for example, let's say I give you, the sum n goes from 1 to infinity of x to the n over n squared 3 to the n. And we want to figure out, what values of x might this converge. So what is an? And I'll call it maybe an of x because it's going to depend on x. What would I call an for this problem? Yeah, x to the n over n squared 3 to the n. Well, I might write this as x thirds to the n over n squared, just to make my life a little bit easier. And so let's calculate rho. If you want, maybe on the previous page, maybe I should have called this rho sub x because it's going to depend on x. So let's calculate the limit as n goes to infinity of an plus 1 of x over an of x. So that's the limit as n goes to infinity of x thirds to the n plus 1 over n plus 1 squared over x thirds to the n over n squared. All right, so how would that simplify? So we have x thirds to the n plus 1 over x thirds to the n. And then we'll have an n squared over an n plus 1 squared. So what is the x thirds to the n plus 1 over x thirds to the n? What does that become? That becomes x thirds. And then we have n squared over n plus 1 squared. What do you think n squared over n plus 1 squared is going to go to? 1. I can actually write this as it's 1 over 1 plus 1 over n squared. I can bring the n squared down below. Or if you just think about it, as n gets really, really large, n plus 1 squared is n squared plus 2n plus 1. The amount I'm different by is negligible. So the limit of a product is the product of the limits as long as at least one of them is finite. So this is going to be, the limit as n goes to infinity of x thirds, the limit as n goes to infinity of 1 plus 1 over n squared. So this is equal to x thirds. So when is this going to be less than 1? So, no, you're close. Yes. So if the absolute value of x is less than 3, then rho of x is less than 1 and converges. If the absolute value of x is greater than 3, then rho of x is greater than 1 and diverges. Okay. So this is how we would use rho for this. And so if I give you, the sum of x to the n, n squared 3 to the n, and goes from 1 to infinity, and then say the sum and goes from 1 to infinity, x to the n over n 3 to the n. So this converges if the absolute value of x is less than 3, converges if the absolute value of x is less than 3, diverges if the absolute value of x is greater than 3, diverges absolute value of x is greater than 3. So what is left to study?
Equal to
So when it's equal to 3. So how could the absolute value of x equals 3? What are the possibilities?
-3 or -3.
3 or -3. So if the absolute value of x equals 3, we have the sum of 1 over n squared, or the sum of -1 to the n over n squared. Both converge. Now over here, if the absolute value of x equals 3, we have the sum of 1 over n, or the sum of -1 to the n over n. What's true in this case? Yep, so diverges, converges. So it converges if and only if -3 less than or equal to x strictly less than 3. And here it converges if and only if -3 less than or equal to x less than or equal to 3. So sometimes when we're using these tests, we can't immediately analyze it to what's going on at the very boundary. Now for this problem, I don't really need to use the ratio test. When I'm looking at this, it's screaming, compare it to the geometric series with ratio x over 3. And that will be larger. So if I'm trying to get convergence, I'm going to be fine. Interestingly, if I move the n squared up to the numerator, it would still converge if the absolute value of x is less than 3. So if I had n squared upstairs, it would still converge from the absolute value of x less than 3. It would now diverge at both plus and minus 3. But the reason is because if I move the n squared from the denominator to the numerator, it's still going to give me a factor in the ratio that is just 1 in the limit. This is a nice exercise. Show the sum of n squared x to the n over 3 to the n converges if and only if the absolute value of x is less than 3. So moving the n squared upstairs is not going to make any difference. Okay, so this is the ratio test. The next one is the root test. And so you will have the sum and goes from 0 to infinity, of an, and let rho equal the limit as n goes to infinity of the absolute value of an to the 1 over n. And if this is less than 1, it converges, greater than 1, it diverges, equals 1, no information. So the proof is extremely similar to the proof of the ratio test. Again, it's trying to find what's going on. And so I'm not going to bother going through the proof of the root test. If you want to see it, email me. I'm happy to either work it into a future class or just give you a lecture on how you do it. Or if you want to try your hand at it, it's a really nice exercise to see, can you prove the root test? And again, it's going to be very similar where you want to relate, okay, eventually the ratio has to, these roots have to be converging to rho, which is less than 1, so I want to have things separated. It's a little bit harder, it's a little bit more algebra, but it's still doable. Let's try to use the root test in practice. So let's consider the sum, n goes from 0 to infinity of x to the n over n factorial. So what should an of x be?
X to the n over n.
Yeah, same as before. And let's see if the root test can do anything here. So rho would be the limit as n goes to infinity of an of x to the 1 over n. So it's the limit as n goes to infinity of x to the n over n factorial to the 1 over n. So that's your value. So it's the limit as n goes to infinity. All right, if I have x to the n to the 1 over n, what is that going to be? X. So I'll just have the absolute value of x for the numerator, and then I'll have n factorial to the 1 over n for the denominator. So it's going to just be the absolute value of x times the limit as n goes to infinity of n factorial to the 1 over n. I'm going to just divide by that. And I'm going to use the limit of a quotient is the quotient of the limits. So it all comes down to, what do you think n factorial to the 1 over n will be? So let's get us some data. Let's try 40 and plus 2 list and then we'll do factorial 1 over n. And by doing it as one point, that's going to make it just numerical approximations. And then what I'll do is I'll do list plot. So what does this seem to be going to? It seems to be going to infinity. And so if I'm dividing by this, it strongly suggests that this should be converging for all values. So we would conjecture that the limit as n goes to infinity of n factorial to the 1 over n equals infinity. Yes. How do I have the intuition to do what? Well, I mean, so I'm going to show you a proof in a second. But one thing is, just your default should be, let me plot it, let me gather data, let me be an experimentalist. And then if you have some data, that can easily influence what you do. So I strongly always recommend gather data. And then of course the question becomes just how much data can you gather? So for instance, if I go back here, and I love how I have to do stop share and keep going slowly. Instead of going up to 40, let's see if I can go to 400. I can go up to 400. I go to 4,000 without too much trouble. 40,000. At 40,000, because I'm saving this as a list, there are issues with how long it takes to work with a list. And what you can do, something like this, this is taking too long and I'm impatient. So what I'm going to do is n. And so I'm now just doing it every 100th. And again, because I have so much data, it's not, I'm not expecting some strange behavior. So if I want to add, 2 more zeros here, 2 more zeros over there, let's do it every 10,000 and see if this is enough so that I can get, and again, this is taking too much time on board. So I'll put another 0 over here and do it every 100,000. And again, you can do some timing and get a sense of just how long it's going to take getting forward. So I'll do it every million. Yes.
What is the cache mode?
Oh, that was on the previous one when I aborted the calculation. That just means it's aborted. It just means I canceled the operation. I got impatient. Yes.
Can you talk about like knowing when to use the different tests?
Yeah, so I will remind me after I finish doing
Okay.
the root test to go back to 1. So here I'm doing it every 400,000. And again, if you look at this, this actually looks, not quite linear, but pretty close. And this is enough to really give you a sense of what's going on. And so again, you can play games like this to get a sense of how it's changing. All right, so let me go back and share. So now, let's study the limit as n goes to infinity of n factorial to the 1 over n. I believe it's going to infinity, right? Because I have some data. So since I believe it's going to infinity, do I want to try to get a lower bound or an upper bound for this? I want upper bound. So I'm trying to show that this goes to infinity. If I get an upper bound for this, will that help me show that it goes to infinity? No. I know that its value is at most plus infinity. Okay. So if I don't want an upper bound, what do I want? I want a low bound. So expect limit is infinity. So find a lower bound going to infinity. So n factorial equals 1 times 2 times n halves plus 1 times n, which is greater than or equal to roughly n halves to the n halves. Right? I'm basically just saying, I take all the terms And for all the terms over here, replace with n over 2. Yes, maybe n is odd and this is a little bit off, but it's, you can make this work. I'm not really concerned. Does everybody understand what I'm doing? Just for the last half, if you just replace every factor with n over 2, you've made things small. So that means then n factorial to the 1 over n is going to be greater than or equal to n halves to the n halves to the 1 over n. Well, what do you do if you have, something to the a and take that whole thing to the b? How do you combine exponents? A, b, so I multiply them. So this is n halves to the n halves times 1 over n, so that's n halves to the 1/2, which is equal to the square root of n over 2, and this goes to infinity. So we see that this will be going to infinity as expected. And my intuition that it's going to infinity allowed me to say, let me just try to find a decent lower bound. I just need a lower bound that's so big that when I take the nth root, it's still going to go to 0. At this point, there's no wrong answer, but some answers are more right than others. To paraphrase Animal Farm. All the animals are equal, some animals are more equal than others. The ratio test and the root test, they're both wonderful tests. If you had a choice, which one would you rather do first? Ratio. The ratio test usually has easier algebra to do than the root test. And so, the question was, how do I determine which order to do things? Well, you go in, which do I think has the greatest chance of working with the least amount of effort on my part? Comparison is the easiest if you can just quickly look at this and see what to do. This is the method of divine inspiration. And so if you know what to compare it to that. This is like if I give you a polynomial, quadratic and ask for the roots, if you can just look at it and factor it, look at it and factor it. If you can't, then what's your go-to? Quadratic formula. And so I would do comparison first. If I have a sequence that's non-increasing or non-decreasing, and I replace the index n with x, and I have a function that's easy to integrate, I might do the integral test. If I then have to resort to ratio and root test, I would almost surely do the ratio test first before the root test. The ratio test is a little bit more powerful. I believe every time the ratio test works, the root test works, but there are sometimes the root test works and the ratio doesn't. So we know a nice function where the ratio test gives us no information. What is that sequence where the ratio test gives us no information?
The 1 over n squared.
Or a little bit more before that, before 1 over n squared.
1 over n.
Yeah, 1 over n diverges, but ratio test is useless. It gives, rho is the limit as n goes to infinity, 1 over n plus 1 over 1 over n, which is the limit as n goes to infinity of n plus 1 over n, which is just 1. So, given that the ratio test is useless, what should we do? Yeah, let's try the root test. So try root. So I am root. All right, let's see what happens. So we would have rho is the limit as n goes to infinity of 1 over n to the 1 over n. So that's the limit as n goes to infinity of 1 over n to the 1 over n. So it's 1 divided by the limit as n goes to infinity of n to the 1 over n. Okay. What should I do? Anybody have any thoughts about what n to the 1 over n does? Or any idea of how we might be able to get some thoughts?
I would say that it would go to 1.
Okay, and how might you confirm that? Yeah, we could try graphing, right? And I have this code. So instead of doing n factorial to the 1 over n, I just delete the factorial sign. And I'll delete. So this would be every 40,000. And let's try every 4,000. And again, I don't really care so much about what's happening in the beginning. Okay, so I see I'm going from 1.00035 to pretty close to 1. So I think this is strong evidence that n to the 1 over n is converging to 1. Yes? And again, this is the power of being able to write really simple code. Oh, so I'm going to stop the share. I think it actually just makes it. It just makes it. Right. So if I look at this, it is suggesting that this limit is 1. So suggests limit is 1, thus would get no information. So sadly, if the limit is 1, the root test will fail in this situation as well. And by looking at this, it's definitely going to. All right. So now we need to prove that the limit as n goes to infinity of n to the 1 over n equals 1. Does anybody have any? Yes.
Would you take e to the log and
So you could do that, yes. I was going to take the log of this and then exponentiate, which is the same as exponentiating the log. So you need to do one or the other. So in my last class, I had a lot of homage to Henry David Thoreau. Why do I like Henry David Thoreau? Simplify, simplify. Actually, it's just simplify, simplify. But simplify, simplify should be simplify, simplify. No, it was just simplify, simplify. And so here, I think this is the right. Insert this one. So Pavlov. So whenever you see a product, you should always be thinking logarithms. So see product, think logarithm. So if I study the limit of the log of n to the 1 over n, and then exponentiate, that solves the problem. Well, what's the log of n to the 1 over n? So what's the log of n to the 1 over n? Remember your log laws. Yes, so I'm going to write it as the log of n over n. And when you see this, we have infinity over infinity. So what should you be thinking? L'Hopital, you know you've made it when your name is a verb. Okay? When you can talk about L'Hopitaling something. All right, so we use L'Hopital. And so this is going to be the limit as n goes to infinity. What's the derivative of log of n? 1 over n. And the derivative of n is just 1. So this is just the limit as n goes to infinity of 1 over n equals 0. So the log of n to the 1 over n converges to 0. So n to the 1 over n converges to it has to converge to 1. So if the log of my number is converging to 0, then my number has to be converging to 1. And that's the proof that n to the 1 over n is going to 0. I mean, if you think about it, if you take n to be, say, 1024, which is 2 to the 10. So your intuition. Let's say we have n equals 1024 is 2 to the 10th. So n to the 1 over n would be 2 to the 10th to the 1 over 2 to the 10th. Right? And if you think about what's going on, if you take the 10th root, you're at 2. And how many roots are we taking? 10th root gets us to 2. We're taking over 1,000 roots. What does the 20th root get us to? So if the 10th root is 2, the 20th root would be not 4.
1 over 2 back.
No. The 10th root of my number is 2. So the 20th root would be the square root of that. It would be root 2. The 40th root is the 4th root of 2. The 80th root is the 8th root of 2. And you can see, oh, okay, yeah, this is like hitting the repeated square root button on my calculator. This is going to, if you've ever done this, this is going to rapidly converge to 1. It doesn't matter if you start above or below. Okay, so this finishes off, I think, all of our discussions on the different types of series tests. And I think next we start moving to Taylor series. And again, the reason we spent all this time on sequences and series is we want to be able to talk about the fact that when we write down these infinite sums, they converge. And I think we talked about the function e to the negative 1 over x squared. Did we mention this function? All of its derivatives are 0 or 0, but which means the Taylor series would be identically 0, but this function is not identically 0. This just indicates that really strange stuff can happen that we have to be careful about. All right, so this is a good place to stop.